talk, I think, has set a perfect stage for my talk. I don't need to talk about how VR, what's VR, what's CBT. So that's great. Thank you. But before I start, I have to admit or disclose that my work has been focused on functional network, brain functioning, but more in the developmental area. We haven't done anything specific to VR or pain regulation. So I have to remind you that you might not be able to take back better understanding of how VR works in the brain or pain regulation, but I will show you some of our perspectives based on our own studies of looking at different functional networks in different other brain states, and also some others work like brain emission, some pioneer Doug Hoffman's work, back in the early 2000s. We think putting all those things together, we have a case for some strong hypotheses, but let's see. In terms of neuroimaging as a tool to hopefully understand how VR works and how we using VR for better pain regulation, the primary tool we're going to use is functional MR. I'm just curious, how many of you have heard or know about fMR? Raise your hand if you have. Oh, great. I think we have more than half, so that makes my life a little bit easier, but I'll go through the basics of fMRI. Basically, we put a subject into an MR machine, and we want to give a stimuli, like, in this case, a monkey, you give it a banana, you will elicit some brain activity. And you design your experiment in terms of, you put the stimuli on and off. There's a, time-locked presentation of the stimuli, and you want to find the brain area that are showing this kind of time-locked activity changes, locked to the task design. So those areas will be called functionally activated by the stimuli. And that's how traditional fMR works in terms of looking at specific brain regions responsible for specific task or stimuli. However, one limitation for this approach is you can only look at isolated brain activity, but we all know that our brain works as a system. Different brain regions from different parts of the brain actually work together make a coordinated effort for a specific function, and which this approach doesn't have the power to really do. So there's a transition from activity to connectivity. So this, using this approach, we not only look at, how different isolated brain regions work in response to stimuli in a kind of toy-like, experimental-like setting, but we can put a subject in a scanner without any specific instructions, just to do in the resting state. We so-called the resting state. You can freely wander, through your own thoughts, and still our brain is working, right? Our brain never rests. Even during sleeping, our brain works. So, and we can, instead of looking at this time-locked activation, we actually look at, how synchronized the brain's activity, different brain regions' functional activity are. So if you look at the green and red curve, these two signals from two different parts of the brain, they are highly synchronized. And by the principle of neurons that fire together, wire together, these two regions are highly likely that they are working together towards a specific brain function. So that's, that's the so-called functional connectivity principle, and that's how we define functional networks. So basically, a collection, a set of regions that show synchronized brain activity during the particular period of time. We call it, they are forming a particular functional network. And this is the primary tool we are going to using to tackle this, better understand the VR mechanism in the brain. And so I will start by introducing 4 of the brain's most important networks in my mind that are, that they're likely play a significant role in how VR can change our brain. So the first network, so if you can see here, in this, look at the brain, there are, red colors and blue colors. And so they represent 2 functional networks. And the red ones are the so-called default mode network. It has the, major hubs in the posterior cingulate area, medial prefrontal area, lateral parietal area. And this network, we call it the default mode network, and it's mainly responsible for all the self-related thoughts, self-referential thoughts, planning, ruminating about your past experience, thinking about the future, anything that's related to yourself. So we, in this talk, I will term this as an easier word is the self network. It's kind of your internal thought network. And then the blue area, the blue network, in contrast, is responsible for dealing with external stimuli. Like you're doing sports, you're doing calculation. These are in the lateral parietal, supplemental motor area, lateral temporal area. So these are called dorsal attention networks. So it controls your attention to external stimuli. And so it's, for the ease of term, I will call it the outside network in this talk. So naturally, you can see there's a contrast, right? One is focused on the internal yourself, the other is focused on external. And there's a natural competition, and you can see their brain activity profiles. The blue curve and the red curve, they are highly anti-correlated. So when one network is up or active, the other network is down. That's natural for us. If you are immersed in your own thought, it's hard for you to pay attention to the external stimuli, right? So it's really, you would think there's also going to need some kind of regulator or judge between these two networks for you to selectively pay attention, right? For example, if you are immersed in your own thoughts, you are planning something related to family or in the future, you tend to ignore the ongoing outside, like the noise, the people passing by you, because your brain judges that your internal thought is more important at that moment. However, for example, if this room there's a fire going on somewhere, then you will immediately switch your attention to the fire, and your brain will tell you run away, because that's more important, right? So here is the network that we hypothesize. This is the CNS network, which centered in the anterior cingulate area, anterior insular area. We call it the salience network because this network really is responsible to evaluate the salience or importance of the events, both internally and externally. And by attaching the same salience value and talk to the executive control network, these two networks work together to flexibly switch our attention to either focus on ourselves or focus on the external stimuli. So that, these four networks as a talk, really, to me, lays the foundation of how our brain really works, both towards the internal stimuli and external stimuli. As Omar mentioned, I just remember two keywords from Omar's talk in terms of how VR works. The first word is escape or distraction, right? So basically, you switch your attention from your internal feeling of pain or distress, things like that, and focus on external, more exciting stimuli. And that's how these two networks can play a role to kind of regulate these two and maybe enhance the interaction with the outside network to focus more attention on the outside events. And then on the other hand, the other word I heard is control your thoughts, right? Pain is inevitable, but suffering is not. That's a very, very, very nice summary. So even if you're feeling pain, you don't necessarily feel suffering. And that's how you want to control your own thoughts. And this is how these two networks, the salience network and the executive control network, can potentially work with the self network and to regulate your own thoughts and think the things in a more positive way, accepting the pain, think in a more positive way, and change your reaction towards the negative stimuli of pain. So that's, so this is our approach, this is our hypothesis, this is our approach. And we have some preliminary evidence, although, as I said, in our work, we didn't do anything specific to pain, but we did other tasks to show you that these networks actually are flexibly interacting with each other, switch your attention towards different stimuli. So here we go. This is a simple task. We did a 3-task experiments. So this shows you the network interaction pattern during the resting state. So the subject is in the scanner, doing nothing, no particular instructions. And this is the frontal parietal control system. This is the combination of the evaluation and control network, so the frontal parietal control system. And this is the dorsal attention network, which we term as the outside network. This is the default mode network, which we term as the self network. So this is, the resting state, there's not so much going on, right? You see the red lines are positive connectivity, blue lines are negative connectivity. You see a more or less balanced connectivity pattern. There are both positive and negatives here going on, relatively balanced in these two arms. However, you do see this outside and inside, they are always negatively correlated. They are already competing with each other. So this is resting state in a more or less balanced state, but if we ask the subjects to do a more external attention focused task, like a certain rhythm of finger tapping. You have to control your fingers in a certain way to do a rhythmic finger tapping. And so that's what we did. And you look at this, this is the network pattern during the finger tapping. And you see much enhanced connectivity between the control system and the outside system. And anti-correlation or a kind of inhibition of self-related thoughts. That's expected because we want to focus on attention to do the external task. We want to inhibit the internal thoughts to be able to perform that task. So that's expected. And then we want to test the other direction. Like if we ask subject to do an internal thought-driven task like a movie watching, because when we watch a movie, we tend to think about ourselves, think our relationships, think about the relationship in the movie. So that's what we did. And there you go. You see the pattern is completely the opposite as you showed here. So the control system enhanced connectivity with the self network and decreased connectivity or show negative connectivity with the outside network. So this is one of the works we did this work. Some other groups also did other tasks and show that this control system actually is flexibly regulating the internal self network and outside network to switch our attention to those stimuli that we need to pay attention to. And this is another task. I won't go into the details, but still same story. The control system and the evaluation network, they flexibly engage or disengage the self network and outside network for certain tasks. So this, based on those, as I said, this comes to our hypothesis that these four networks are the fundamental elements in the brain that we think we are, is a kind of a gateway or a channel that we are may potentially impacts or change our brain, change how we perceive pain, and like through distraction or escape, using this arm between the control system and outside network, like by switching your attention to the external, more exciting stimuli, that you naturally forget about the internal suffering. Or on the other arm, you can do it's actually it's a different mechanism. Then you can enhance the control of your own thought and change things from negative to neutral or even positive side of things. So this is our hypothesis, and there are actually yes. So I don't want to read this. Just to reiterate, this is our hypothesis, and then so how exactly talking about pain, these network level interactions has to do with pain. And there are existing studies, not from our group, from other studies, and this is actually a review paper showing the kind of the common, I think we have a consensus on what are the brain regions that are involved in the pain processing. And as we can, although this is again, this is more from the traditional fMRI task or things, histology. These are individual regions, but if we look at these individual regions, we can see these are areas. The thalamus, obviously, it relay the signal from the body to the brain and to the primary sensory motor area and to the posterior insular area for initial pain perception, and then to the amygdala, which is the emotional center of the brain, to get an initial appraisal of the emotional salience or emotional importance of the pain stimuli. A lot of times it's negative, right? And then if you go up the stream, there are these anterior cingulate regions, which I talked before. This is the center. This is one of the hub area in the salience or in the evaluation network. And then this is the medial prefrontal area, which is a hub in the self network. So we can, with the pain signal from the amygdala or posterior insula, may go to these two networks and combine your own experience, own memory, and do a first-level evaluation of the emotional salience, importance evaluation of the pain signal. And then further up the stream, you have the regions within the control system, the control network, which is you see the dorsolateral prefrontal, ventrolateral prefrontal, and optofrontal areas. And these areas is at the top of the control hierarchy and can work with the CNS network, the evaluation network, to really gauge the importance, or in this way, it can actually, change your thoughts. By working with the evaluation and self network, it can really try to, as Omar said, as we know about how CBT works, to try to let your brain identify the pain, accept the pain, and challenge the negative thoughts associated with the pain, and become more open to it, and sometimes even be more positive to it. Like Brandon yesterday said, no pain, no gain, right? If you think pain that way, I'm experiencing pain to get some gain. So you can use your own self-regulation ways to achieve the goal of changing your perception of pain. So pain is painful, but you don't need to be painful in your mind. You can change your mind and change, so that's how the CBT from this chain of actions can change your own thought and change your perception of pain. And we do have some preliminary evidence on this route of action. And there are works done in 2012 by Jensen et al. They show that after 8 weeks of CBT therapy, using the same principle as we just said, change your own thoughts, and they see increased activity in this dorsolateral lateral prefrontal area, which is in the control network. So which is kind of evidence supporting our hypothesis. And then there's another work. In 2017, they also showed after CBT therapy, there's change in the anterior insula, which is the hub of the evaluation network. So these are the really from the studies from other groups that support our potential hypothesis. Although they are looking at individual regions, not in a network way, but these are exactly the hub regions of those networks. So naturally, we would think, if we look at from the network perspective, we would get more insights into how really this works. And then, so yes, so this is the arm, and we hypothesize, and we have some preliminary evidence, and then we can look at the other arm. So besides these regions, there's another here. This is the supplemental motor area, which is actually another region in the outside network. So that leads to another way of a chain of action, that the potential, the control network can work with the CNS network, and outside network can distract your attention and focus, rededicate your attention to external exciting stimuli. So that's the aha or escape moment, that you forget about the pain you are experiencing and focus more on outside. And also, we do have evidence to, I think this is the work that Brandon mentioned by Dr. Hoffman et al. In the early 2000 about, using VR, how our brain changed after VR therapy. If you see, the first column is the brain activation. There's no VR, no opioids, so this is the brain activation during pain. And you see a lot of the activities, the red activities going on in the first column. And then the second column is with VR but no opioids. The third column is with no VR but opioids. The fourth column is VR plus opioids. But if you focus on the middle two columns, with VR or opioids alone, they are almost identical to achieve a similar degree of decreasing in terms of brain activity in response to pain. And in this experiment, they put the subjects on a VR set and in an ice channel, beautiful ice channel that really want to achieve the escape effects. And you see the dramatic decrease of brain activity related to pain perception. So I think this is a strong evidence to tell us that this arm also is one of the one of the two arms that VR can potentially work: distraction, escape, and self-regulation. So how does the VR and CPT reduce pain? Exactly, as I said, we haven't done this, this is our hypothesis. We haven't done anything specific doing experiments, but, so we don't know, but we do, this is our hypothesis, the two arms that I just talked about. Hopefully, I did, it convinces me. I'm not sure if it convinces you, but this is our starting point. We will test this kind of network level hypothesis in terms of how VR combined with CBT may reduce pain perception through the two arms. One is distraction, the other is enhanced self-regulation. And in our work, me, Brandon, and Caroline is going to talk about us. We come up with this more kind of unified brain-body model. So I talked to you about how VR may impact brain and how brain may impact pain through this four network level kind of interaction model. But there's potential, I think that when I need to use the word potential, there's another pathway that the brain, the cortical networks can interact with the hypothalamus area, which is the keynote of the HPA axis, can lead to improved stress immune response in chronic pain, and in turn reduce pain perception. I will not go into details because Caroline is going to follow my talk and talk about that aspect, to talk about our unified brain-body approach. So with that, I conclude. I thank Brandon and Caroline who worked together on this proposal to try to really better understand the mechanism of pain through a unified brain and body model. And thank my postdoc for the work. And as I said, I focus on other areas. So this is my whole lab. Thank you so much.